if a substituent does not have a lone pair bearing atom bound to the ring, then you only need to think about inductive effect in general. Okay, but if you do have a lone pair bearing atom, let's say make it more general. Okay, if if the substituent does not have a sp2 hybridized atom bound to the ring, then you only need to think about the inductive effect. And this oxygen is actually sp2 hybridized, because where it's sp2 hybridized, the lone pair can be donated to the ring. It can have a better delocalization of electrons. Okay? Now in case of this oxygen, and the many lone pair bearing atom, the two electronic effects, they actually competing with each other. Inductive effect, okay, and say resonance effect. And the importance of resonance effect mostly relate to the stability of this resonance form. So this resonance form stability impacted by mostly how strong this carbon heteroatom double bond is. Here is carbon oxygen double bond. If this carbon oxygen double bond is very stable, then this resonance form becomes relatively important. That means this resonance electron donating effect is stronger. Okay, so this bond strength is mostly relate to the length of this bond. So the shorter this bond is, the stronger this double bond gonna be. Okay, and what determines the length of this double bond is we know one of them is a carbon atom is fixed, right? That means the size of the other atom. Okay, so that's why those second period elements, okay, they can form relatively strong double bond, because you have a second period element, the carbon and that atom double bond is relatively short, so very strong. Okay, so what are the second period elements? They can form. We can have lone pairs, 3: nitrogen, oxygen, and fluorine. Okay, and then out of those 3, then we think about it. The two effects are competing. One is the inductive effect. One is the lone pair effect. So inductive effect is determined by virtue of electronegativity. So the more electronegative this element is, the inductive effect is stronger. Okay, so that's why if you look at the 3 groups, say these 3 substituents, okay, which one has the strongest inductive effect? Most all these groups are, when you look at the inductive effect, all of them are electron withdrawing. Okay, but which one has the strongest electron withdrawing inductive effect?
Fluorine?
Yes, very good. Fluorine, because as we all know, fluorine is the most electronegative out of the 3. Fluorine, oxygen, nitrogen. Fluorine more electronegative than oxygen. Oxygen more electronegative than nitrogen. Okay, so that's why But as you will see later, even fluorine, okay, the inductive effect is more or less similar to its lone pair effect in terms of electronic effect. They are very similar in case of fluorine. So the fluorine is already the most electronegative element. Has the strongest inductive effect here. Okay, so fluorine inductive effect and the lone pair effect, they are pretty much the same. Okay, as we're gonna see later. So for oxygen and nitrogen, the lone pair effect always overrides inductive effect. Okay, so that's why if you have oxygen or nitrogen, you have a lone pair bound to it. Have a lone pair on it, bound to a ring. They're always very strongly activated, because the lone pair effect far outweighs the inductive effect. So fluorine, these two effects, they are pretty much the same. Okay. In case of fluorine, they are pretty much the same. So fluorine, the lone pair effect, electron donating, inductive effect, electron withdrawing, they are very similar. Okay? They are very similar. Okay? That's just reference standard. Memorize something. Fluorine, the lone pair, the resonance electron withdrawing effect. Okay. I'm sorry. Resonance electron donating effect and the inductive electron withdrawing effect, they are pretty much equal. So this reactivity is similar to just unsubstituted benzene. Then the oxygen, nitrogen, they have a substantially weaker electron, inductive electron withdrawing power than fluorine. So those two guys, the resonance electron donating effect far overpowers the inductive effect. So makes oxygen and nitrogen, those two are very powerful activating group. And out of these two, can you tell me which one is a more powerful activating group? Basically, more electron donating will be more powerful activating group. So the nitrogen version is more powerful, or the oxygen version is more powerful. So overall electronic effect is a combined, the summation of two effects. Okay, one is a resonance electron donating. Okay, the other one is the inductive effect, electron withdrawing. Okay, so in all those three guys, the inductive effect, electron withdrawing, resonance effect, electron donating, and the inductive effect, this is strongest, this is the weakest. Okay, so overall, which one is the most powerful activating group out of those two? Let me call someone. Nadia. Oh, very good. Okay, because the lone pair effect, they are similar. Resonance effect, they are similar. Okay, but nitrogen has a weaker inductive electron withdrawing effect. So nitrogen is the most powerful one, then followed by OH. Okay. So this discussion will be useful later on. So the most powerful are all nitrogen based. Okay. Oxygen is a bit weaker, but still very powerful. Okay. And why those two guys are a bit weaker? Because of, keep in mind, carbonyl group is electron withdrawing group, right? I made an argument that carbonyl doesn't matter the inductive effect or resonance effect. Carbonyl group electron withdrawing group. So yes, we know the nitrogen is the electron donating group. Okay, but some of those electron donating power will be given to the carbonyl group. So this electron donating power will be shared between the aromatic ring and the carbonyl group. So this one is a bit weaker. Okay, same argument. This one also a bit weaker because of this oxygen is very powerful electron donating, but it will be shared between the carbonyl, its electron withdrawing, and the aromatic ring. Okay. Okay. So these are the most powerful electron donating group and activating group you will be seeing. Okay, and this is a second class of activating one, and this will be less activating than this because you have a carbonyl group connect to the oxygen. Okay, so will be less activating, okay? But still activated because after all, this lone pair can be part given to carbonyl, another part given to the ring. Okay? Now let's look at the directing effect of those activating groups. And as I told you, all activating groups, they are OP directors because all the activating groups, they are electron donating groups. You have electron donating group, they will help stabilize the sigma complex if the electron donating group is directly attached to the carbon with positive charge. Okay. So you can see the same argument about the let's say alkoxy group. What's alkoxy group? You have oxygen bound to the ring. The other part of oxygen connect to LQ group. So this entire group we call alkoxy group. Okay. Now if you have the alkoxy group, if you carry out say meta ES reaction, you can write 3 resonance forms, just like all meta sigma complexes we have seen so far. The positive charge will be never on the carbon directly bound to the substituent. Okay. So all of them are secondary allelic. Okay. Now, if you have the ortho or para, substitution sigma complex, 2 of them are secondary allelic, like we have seen so far, and 1 of them will be tertiary and allelic. Now, what's different here is different from the sigma complex we have seen with toluene. Now this oxygen, this substitute has a lone pair bearing oxygen atom connect to it. So you can write basically an additional resonance form. So in addition to this tertiary and allelic carbocation, not exactly tertiary because it's not carbon, but basically you have an electron donating group connect to a positive charged carbon. Okay. Now, because of this oxygen has a lone pair, you can write an additional resonance form. So the lone pair can be donated to here, and then the positive charge will be on the oxygen. So out of those 4 resonance forms, which one is the most stable one? The bottom 4 of them. I hope you recall those. Let me help you refresh the knowledge about resonance forms. Okay, while you're looking at a set of resonance forms, and if you want to find out which one is the most stable one, and the most stable one will be the most important one, makes the greatest contribution. The rule 0 for resonance form stability is that the form that has the largest number of covalent bonds always is the most stable one. Everything else will be secondary. Okay? Whatever form has the largest number of covalent bonds, that form always will be most stable. Then other things are less important. Okay? If you apply this rule, which form is the most important one? The last one. Okay, very good. Why? Because of compared to all the other the 3, the last one has extra covalent bond because of basically the difference between those 3 and the last one is the lone pair become a covalent bond. Okay, so last one is the most important one. Okay, so that's why because of this additional resonance form, the OP sigma complex, they are much more stable than the meta sigma complex, much more. Okay, so if you have a lone pair bearing substituent, if let that aromatic compound undergo ES reaction, you get an exclusively OP product almost. The meta product is usually less than 1%, usually. Okay, and also there's a heavy preference for P product. Okay, that you don't need to memorize, but just for your knowledge, heavy preference for P product, but almost exclusively OP product. Same thing for the P substitution, because P substitution also you can write a resonance form where positive charge is on the substituent. Okay, and then because of the substituent is a lone pair bearing one, so the lone pair can donate to the positive charge carbon, give you the most important resonance form. Likely you will be asked to write such resonance form in the exam, so make sure you Be very familiar with it. Okay? Now we have finished about all the activating one. Let's look at the the deactivating ones. Okay, standard of comparison always is hydrogen. Okay, so if you replace hydrogen with a halogen, will be deactivating. Okay, we'll talk about later. Okay, and if it's the halo methyl group, they're also deactivating. It's understandable because of halogen, halo methyl group, the atom direct bond to ring has no lone pair on it. Okay, so you only, this is sp3 hybridized, so only need to think about the inductive effect. But because halogen is a powerful electron withdrawing group, so makes this overall this carbon will be steering electron density away from the ring, so it's deactivating. Okay, and then the rest of many substituents, okay, they from here to here, they share, those are 5 substituents. They share a very similar structure. All of them has the carbonyl carbon directly bound to the ring. So all of them are strongly deactivating group. Because we know carbonyl carbon is an electron withdrawing group. It doesn't matter you look at the inductive effect or resonance effect. So it's deactivating. So the strongly deactivating actually. So all this one are deactivating group and the meta director. For similar reason, CN triple bond, cyano group, if the carbon is bound to the ring, also is a strongly deactivating and the meta director. So is the sulfonic acid, okay, group, because this sulfur is bound to the highly electronegative oxygen atom, so it's very electron hungry. So also heavily deactivating and the meta director. So this one, why it's heavy deactivating? Because of this one is bound to nitrogen. Nitrogen is not as electronegative than as oxygen, but it is substantially more electronegative than carbon, and it's triple bound to the carbon. So basically, this carbon will lose a large amount of electron density to nitrogen. So that makes this carbon super electron hungry. So it's also powerful, strongly deactivating and meta director. CF3 we talk about it, okay, and NO2 is actually the one of the strongest deactivating group you'll be seeing. Why that's the case is because if you look at the NO, NO2 is like called more powerful version of carbonyl. Where's my cursor? Can't see the cursor. Okay. Drag here. Computers not helping. So the NO2, if you look at NO2 group, okay, is basically is a bigger brother of the carbonyl group. So you see the this is NO2 group. The nitrogen has a 1 unit of positive formal charge, and the carbonyl group, we know the carbon doesn't have a positive, in carbonyl group, like CO, carbon actually has 0 formal charge there, okay? Although it has a partial, let's say this group, okay? Carbon here does not have a full unit of positive charge. And here nitrogen has a full unit of positive charge. And we know nitrogen is more electronegative than carbon. So based on these 2 arguments, we know nitro group is a more powerful electron withdrawing group than carbonyl group. Okay, so this actually nitro group, is the most powerful, deactivating group you will be seeing so far in an ES reaction. So the why, and the strongly deactivating group, they always meta directors, because as long as you have a strongly, the deactivating group, they are always a very powerful electron withdrawing group. If you have very powerful electron withdrawing group, let's say place here, if it replaces CF3, always going to be destabilizing the positive charge it connects to. Okay, so that means the OP sigma complex will be destabilized with respect to their meta version. Okay, that means the all very powerful deactivating groups, they are all very powerful electron withdrawing groups. They are, all of them are meta directors. Nitro group is a meta director as well. Okay, so let's just look at a few examples. Let me just I want you to judge whether the first, this reaction will give you what product? This reaction condition. What kind of reaction you expecting from this reaction condition? Bromination, okay? So bromination will be happen to the ring. But the question here is, will the bromine will be installed on the ring? Meta or O or P? OP doesn't matter, always go together. So except you have a very, very bulky group, okay, that will be go to P. But like this one is not very bulky, so it doesn't matter O or P. If it's OP or it's meta, it's a meta or OP. Basically, this existing substituent is activating group or deactivating group. Please louder. Activating or deactivating? Yes, activating, because you have to look at what is atom bound to the ring. Okay, here is a lone pair bearing atom, oxygen bound, so it's activating. So then that means it's well, doesn't matter O or P, both are correct. Although probably be getting a bit substantially more P than O. Okay. Now next one. Say the first, this reaction is nitration condition. Okay, so where nitro group will be installed into. First, look at this, activating or deactivating. D or A, just D means deactivating, A means activating. Look at what's atom connect to the ring. There's a carbonyl compound to ring. Okay, so it's D or A. D, deactivating. Okay, so if strongly deactivating, so this is a meta director. Okay. So this, those two things are a bit confusing. The substitute structure are similar, but you have to really look at details which atom bound to the ring. If you're lone pair bearing atom bound to ring, with the exception of with the exception of a halogen, they always activate. Okay. So again, bromination condition. where the bromine should be installed onto. So this is what group, D or A? Nitro group is the, see, okay, many of you say activated. Okay. The key part, if you look at the nitro group, do you have a lone pair on it? Do you have a lone pair on it? No, so it's activated or deactivated? Deactivated, okay? So meta. No. This guy is activated or deactivated. This group is activated or deactivated. Yes?
Would it be deactivated because the methyl groups are pulling electrons away from the center?
Methyl group, usually, its effect is minimal. I'm not saying nothing is minimal. Huh? It's actually a lone pair here, okay? It's actually a lone pair here. So this actually is one of the most powerful activating group, okay? So see, if you have nitrogen bound to the ring, usually if you have oxygen bound to the nitrogen, it will be deactivated, okay? But you don't have it. If you have carbon or hydrogen bound to nitrogen, you have to look at whether there's a lone pair here. And you have a lone pair here, very powerful, very powerful activating group.
Are there any cases where it'll have a lone pair and it'll be a deactivated group?
If you don't have a lone pair, if you have nitrogen on it, it will be deactivated.
Yeah, like I'm saying, is there any cases where it will have a lone pair but will also be deactivated?
Only thing halogen. Only halogen. So this is basically all right. So these are some examples. We have the thing about the activating, deactivating, and the halogen is sort of interesting because they are also para directors, but usually considered deactivating. That is because, keep in mind, halogen, that's a group of elements that is most electronegative on periodic table. The group 7, they are most electronegative group of elements. So their inductive effect is always strongest in the same period. In one period, halogens, their electron withdrawing effect always the strongest. Okay, so that's why in general we consider the halogens, they are deactivating because of the electron withdrawing power. In general, they overpower the resonance effect. Okay, so as I showed you, for the fluorobenzene, these two effects, the inductive effect and the resonance effect, they are almost the same. So fluorobenzene and the parent benzene, the EAS reaction rate, they are very similar, okay? But if you look at the chlorobenzene or bromobenzene, let's say chlorobenzene. So we know there's a inductive effect, okay? Electron withdrawing, okay? And also we can have the resonance effect. Okay, but compared to fluorine version, this resonance form for the chlorobenzene, okay, is substantially less stable than this guy, okay? Why? Because chlorine is a third period element. So carbon chlorine bond, double bond, is substantially longer than carbon fluorine bond. So that means longer double bond make it less stable. So that means this form contribution is substantially smaller than the contribution of this form in fluorobenzene. So the lone pair effect, resonance effect of chloro or bromobenzene is weaker than fluorobenzene. Okay, so that makes chloro and bromobenzene, they are actually less reactive than fluorobenzene in EAS reaction because the lone pair effect are much weaker. The inductive effect also a bit weaker, but it's the reduction of the inductive effect is far lower than the reduction of the resonance effect. So that makes the fluoro and makes the chloro and the bromobenzene overall less reactive in EAS reaction compared to the fluorobenzene. Okay, look at the fluorobenzene. If you look at all the sides, okay, if add together, the fluorobenzene, the reactivity add together is 4 point something. Okay, 4 point something. And if you look at all the partial rate factor of parent benzene is about 6. Okay, so fluorobenzene, the EAS reaction is actually rate similar to the unsubstituted benzene. And the chlorobenzene is less than 0.5, okay? And the bromobenzene is less than 0.4. Mostly because of the weaker resonance effect, where the halogen lone pair donate to the ring. And especially look at the para site of fluorobenzene is actually almost 4 times more reactive than single site in the unsubstituted benzene. Why? Because this site is actually the receive a lot of benefit from lone pair effect or resonance effect of fluorine, the lone pairs, but it doesn't suffer as much inductive effect from the fluorine, because inductive effect, the important thing is the distance dependent. So this site suffers the strongest from inductive effect because it's at the shortest distance of fluorine. This site is actually under the smallest or weakest influence of the inductive effect of fluorine because it's very far away from fluorine. Okay, so that's why this site is actually more than 10 times more reactive than the ortho site. It's actually about 4 times more reactive as a unsubstituted, the benzene. Okay. Let me just showing you that how the positive charge and how the fluorine lone pair can enhance negative charge on the the para side. Okay, so from this resonance form, you can further write here. Okay. See, the negative charge can, by resonance, can go all the way to the para side. And this para side doesn't suffer much from inductive effect from fluorine because it's, the site is at the longest distance to the fluorine. Okay, so that's why fluorobenzene is actually heavily prefer para substitution. And if you look at the 3 halogenated benzenes, they always have the the basic fluorobenzene is the most reactive one, followed by chlorobenzene, followed by bromobenzene, because of the resonance effect from the halogen lone pair. This one is the strongest. This one second. This one third. Is why? Because of the CF double bond is the strongest. Okay, followed by carbon chlorine double bond, because the carbon chlorine double bond is substantially longer, and the carbon bromine double bond even longer. Okay? Now, when it comes to the regional selectivity, you will see it's almost exclusive OP product at together 99%, and the P is substantially preferred. Okay, here. And the why it's substantially preferred. Let me just give, using nitration as one example. Let's say if you do the fluorobenzene nitration, okay, fluorobenzene nitration. In the sigma complex, if it's para one, okay, and you always can write this resonance form. And that's the reason why OP are strongly preferred, because of the additional resonance form. You will not be able to write in case of meta substitution. So this form, okay, you only can write for the ortho or para substitution sigma complex. You will not be able to write for the meta sigma complex. And this form is more important than any other form because of extra covalent bond. Okay. So that means the OP sigma complex can be stabilized by this very important resonance form, and the meta one can't. Okay. That's why, although it's halogen considered as deactivating group, but it's always a very strong OP director. So now we complete all the single substituents, the aromatic compound EAS reaction. Any questions you might have so far? If you don't have a question, let's look at what if we have multiple existing substituents? And let's look at simple cases. Okay. Now in some simplest cases, even there are multiple substituents on the aromatic ring, but all the the potential aromatic sites, they are actually equivalent, like the one we have seen here, the para-xylene, basically para-dimethylbenzene. Okay, although there are two substituents, but it doesn't matter the electrophile attached to which side. All of them will be, also to one of them, meta to the other. Okay, doesn't matter. This one, they are equivalent, so it doesn't matter. Okay, that's the simplest case. But just something else I want to just bring your attention. This acid anhydride and the alumina chloride mixture. This condition for Friedel-Crafts alkylation. Okay, just basically this part, the acyl group will be installed to the one of aromatic side. So this part. And also, in some cases also relatively simple. The two, although you have two substituents on the ring, but both substituents prefer the same site. Like in this case, you have two substituents. One is a methyl, one is a nitrile group. And the methyl group, I hope now you know it's what group? What kind of directing group? OP, good, okay? So you prefer these two sides, okay? These two sides next to it, okay? Because P already occupied. So one of two sides also to methyl. And the nitrile group, now everyone should know it's a meta director, okay? So prefer the two sides meta to nitrile group, also to the methyl group. So yes, the two substituents want the same side. So that again, it's the simplest case, okay? So that's, you don't need to worry about too much. And then now, if in some cases, you might have a few sides as far as directing effects are considered, they are similar. Like here we have two methyl groups, both are OP directors. So this methyl group wanted these three sides, okay? And then let me get the other methyl group. So this methyl group, okay, also wanted these two ortho side and this, the para side. So again, all the three sides, those two substituents want the same set of three sides, same set, okay? Now the thing is like, what is it now? Well, the seems like there's not much preference in terms, because all those three sides are same set of three sides are preferred by the two substituents. But if you look at those set of three sides carefully, they are actually different, okay? Because of the the difference is basically you will see a difference if you consider the stereo hindrance. Because if the electrophile come to here, okay, you will feel the stereo hindrance from both sides, okay. But if the electrophile either come to here or come to here, you only feel stereo hindrance from one side. So obviously, one of those two sides will be more preferred than this side when you consider steric effect. Okay? So that's why you're getting this product. Obviously, you can put the here also, but it's exactly the same product. Okay? Exactly the same product, as you can see. So you put here and put here, the exactly same product. Okay? Now this more troublesome situation is that if you have two existing substituents and they prefer different sets of sides, okay? Like here, this group is an OP director. So P already occupied. So this group, this group prefer this size, okay? Because P occupied. So okay, the top group prefer the two sides also to it. Chlorine, as we know, also is what director? Chlorine is what director? That's a rule. If you have a lone pair bearing atom bound to the ring, always what director? Always OP, okay? It's not always activated, but always OP. If it's halogen, could be deactivating. If not halogen, will be activating. Because if you have lone pair there, always can stabilize the positive charge next to it. Okay, so always OP. So chlorine is OP. So chlorine, the wants these two sides. Okay. Now basically, you have a competing directing effect. Then basically, they depend on whose arm is stronger. Okay. So the rule is that whatever group is a more powerful activating group will decide where the electrophile will be going. So which one is the more powerful activating group? The chlorine or the nitrogen-based group? The nitrogen one, because nitrogen-based group is the most powerful activating group. Chlorine is actually not activating. So yeah, this guy wins. Okay. The electrophile will go to one of the two blue sides. And some cases again, just like the 1,3-dimethylbenzene, steric hindrance will be important if you when the directing power of substituents has no big difference, then you have to consider steric effect. So here both the existing substituents are LQ groups. So their electronic effect, we consider they are the same. They are the same. So the only thing you really consider is steric effect. Okay. So if you consider electronic effect, the left side, okay, tertiary butyl group want these two sides because the parasite is occupied. Okay. Now the methyl group, as we know, also is OP director. So you want these two sides. So electronic effect, they are pretty much the same. So now it comes to steric effect. Obviously, the red sides, okay, they have less steric hindrance, okay, because of any group next to tertiary butyl group will be squeezed. So yeah, you get the electrophile comes to the red side. So basically, we have up to this point, we pretty much learned all the EAS reactions, electrophilic aromatic substitution reactions. Now let's talk a bit about how do we apply those EAS reactions in synthesis of the substitute benzene. And also, I hope take this moment to refresh some basic concepts we have learned regarding the retrosynthetic analysis. How do we apply the retrosynthetic approach into synthesis problems. Okay, and just when if you are facing a synthesis question of substitute aromatic compounds, say substitute benzene derivatives, there are a few things you need to consider. Okay, one is substituents already on the ring dictate regional selectivity. That's basically all what we have been talking about since later last class and the entire today's class. We all talk about this, regional selectivity dictated by the existing substituent. Okay, and certain cases also we must think carefully about the order in which groups are added to a benzene ring. So for instance, you cannot add a meta director if you need to add a substituent para next. Okay, and do not add an OP director if you need to add a substituent at the meta site next. Okay, just for instance, okay, if you are asked to synthesize this compound, name we don't need to worry about. Basically, we have a bromine group and a carbonyl-based group. They are meta to each other. Okay, so if we are asked to making this guy start from benzene, just unsubstitute benzene, just the benzene. Okay, we are asked to make this one, okay? So obviously we need to introduce both, introduce two substituents sequentially, okay? But the question is obviously we need to think is which one we should place first. Now these two substituents, they are meta to each other, right? So the first group you put on the ring must be what director? Meta director, because the two sides, the substituents are meta to each other. So first substituent must be a meta director. Okay, because if we put OP director, then you put a second substituent, then will be OP to the first one. Okay, you get my point? So there are two options. If you put bromine first, okay, then you can install second substituent by Friedel-Crafts isolation. Okay, but whether this one will work, have to think about what kind of directing group bromine is. What kind of director bromine is? Just bromine, I'm not showing here, but you should know bromine has lone pairs on it. So bromine is what director? OP director. So do you think this one will work? This approach work or not? If you install bromine first, will it work? No, because this one will either be here or here, okay? You want it to be here, meta to the bromine. So you think about whether this one will work. If you put the carbonyl group first, okay? What kind of director this one is? Meta. So this one will work. So yes, this one is a right approach, okay? So that's just some consideration you do think about when you really think about the synthesis, okay? And basically for this particular problem, if you basically you start from benzene, you probably can do the acyl chloride, aluminum chloride, and you get gets the carbonyl attached it, okay? Then you do the bromine ion. Okay, that should work, okay? The bromine first, it will not work. Okay? So that's, when you put, if you are asked to put the group substitute sequentially, be careful about the directing effect of the first group you put on. Okay? And the second one, in addition to the directing effect of the first group, again, if you want to ask for the multiple substituents on the ring, also need to consider the deactivation effect of the the first substituent. Okay. Again, if you consider you are asked to make this compound from the benzene, okay. So if you look at the directing effect, they are actually, it doesn't matter you put on this one first or put this one first, because of the both of them are what director? Meta director. Both of them meta director. Okay. So directing effect doesn't matter which one. Okay. So appears like okay, I could put a carbonyl first, do nitration, or put nitro group first, then do the Friedel-Crafts isolation. Both will work. Okay. But there's one thing we didn't really talk about it, okay, before, but now I'm telling you, is basically Friedel-Crafts reaction is is practically speaking, it only works well in the on those activated rings or slightly deactivated rings. Slightly deactivated rings, like say halogenated benzene, it probably work. Okay? But anything less activating than halogenated benzenes, their Friedel-Crafts reaction will be exceedingly slow, not practical. Okay, so if you know that, then you immediately will rule out this approach. Because, as I mentioned when we're talking about the deactivating effect, nitro group is the most powerful deactivating group we have seen so far. So this ring is extremely unreactive in an ES reaction. So if you let this ring, this guy, nitrobenzene, to participate in Friedel-Crafts reaction, maybe take 5 years to have 5% conversion. Okay, so you won't work. Okay, so that's just for the rate consideration. So you have to do Friedel-Crafts first, then nitration, because nitration is actually nitronium cation. Again, is something See, it's actually relevant. Nitronium cation is one of the most powerful electrophile we have seen so far. Most powerful electrophile. And the most powerful electron withdrawing group, they are actually going the same line. Why they are very powerful electrophile? Because they are very hungry, want to get react with the the electron pairs. Okay, that means if you connect to some substitute, they will steal electron density like like there's no tomorrow. Okay, so that makes the ring extremely unreactive. They are going the same line. Okay, so the nitration can work with any aromatic compound, except something we're going to tell at the end of the semester. If those aromatic compounds are too reactive, nitration could be an issue actually. Okay, but that's not something we're considering now. Okay, but for at this point you can say, oh, nitration can work with any aromatic compound. For at this point, okay. So yes, this one is a real approach. Okay, this one won't work because Friedel-Crafts reaction only works. Okay, for those the at the most weakly deactivated rings. Generally, you prefer some the activated or at least just the not deactivated rings. And in some the synthesis process of the aromatic compound may involve additional functional group manipulations. Okay, for instance, okay, if you are asked to make this compound, okay, from toluene methylbenzene as a starting material. So obviously, the first step you can do is look at the compound, right? The target product under the starting material. Obviously, you need to introduce a nitro group. Okay, so yes, under you just do the nitration, you can get this compound. So if we always assume that we will be able to separate O and P product because they always go together, as far as mechanism goes. So we always assume if you ask for synthesis, you always can assume you can separate O and P products. Okay. So here, you do nitration, you get O and P product, you separate the P, then, but I wanted this, not the I want this guy, not this guy. So we have to do some additional functional group manipulations. So we have to convert this group to this group. This called carboxyl group. I mentioned maybe one class earlier. Okay, this carboxyl group. But how do we convert methyl group to carboxyl group? That's a reaction we learned in chapter 12. Okay, in organic 1. If you forgot that, just review a little bit. So here is the process. So the nitration for nitro group, then take the Jones reagent, I believe it is called, the chromic acid, pretty much. Then you will oxidize the methyl group and the carboxyl group. Or any LQ group has a benzylic hydrogen will be oxidized by the Jones reagent into carboxyl group. So that is the synthesis. most of EAS reactions. Then we're going to also talk a little bit of substitution in naphthalene. So the naphthalene, if it's unsubstituted naphthalene, they actually have two kind of sites. One is site 1, this is site 2. This another site 2, this another site 1, this another site 1, this another site 2, this another site 1, this another site 2. Basically, two types of sites. Okay? So the substitution is faster at carbon 1 because of the corresponding, the sigma, the complex, is a bit, more stable. Okay, so that's why the attachment at the carbon 1 is a bit faster at the carbon 2. So why this one is more stable than this? Because if you look at the resonance forms of the sigma complex, you see the sigma complex, when you electrify attached to carbon 1, in these two resonance forms, you don't need to break the aromatic ring. Okay, but here only one resonance form you can keep the aromatic ring. All of others you have to break the aromatic ring. Okay, so basically this gives this guy better the stability. Now the heterocyclic compound, they also can undergo EAS reactions. So what I mostly want to discuss is pyridine and pyro. Okay, and if you recall in organic 1, we already discussed the difference between pyridine and pyro. So the pyridine, the major difference when we're learning organic 1 is the pyridine, the nitrogen is highly basic, it's kind of basic, and the pyro, the nitrogen is not basic. Okay? So that because of nitrogen has this lone pair available in pyridine, but the pyro, the lone pair is needed for the ring to be aromatic. But here, when we compare pyridine with benzene, what you see is the pyridine is otherwise same as benzene, except one of the ring atoms replaced by nitrogen. So as we know, nitrogen is more electronegative than carbon. Okay? So and this lone pair, unfortunately, this lone pair is in sp2 orbital. So this lone pair cannot make any contribution to increase the pi electron density because this lone pair is not in the p orbital, it's in the sp2 orbital. Okay, so it cannot help to increase the pi electron density. Nothing. Okay, now because of nitrogen is more electronegative than carbon, so nitrogen can attract the pi electron towards itself. So makes the pi electron density on pyridine is substantially, you guess, lower or higher than the aromatic ring. If nitrogen attracts electron towards itself, then the pi electron will be more available or less available to do EAS reaction. Less available. So pyridine is substantially less reactive than benzene. So just if you can treat the pyridine just like a nitrobenzene as far as the EAS reaction is considered, is just like nitrobenzene. And pyridine, if you need much let's say there's stronger reaction conditions than benzene to undergo similar type of the EAS reaction. For instance, in case of benzene, if you're on the sulfonation reaction, just sulfuric acid reaction will happen. But if you want a pyridine to undergo same reaction, you need to add sulfur trioxide and add mercury sulfate as a catalyst and heat to very high temperature, then reaction can happen. And And also the pyridine, you know, preferentially always on the ES reaction happens at the carbon 3 side. Means nitrogen is a number as a first atom, okay? Nitrogen is the first atom because that's a unique atom. Nitrogen is 1, this is going to be 2, this is 3. So all ES reaction of pyridine happen at the C3, so-called.